Alrighty. Sound sync. Alright, I got a couple of these guys here. I can stack them and fill in these holes here. Pi is powered down, right? Yes. Get out of there without wrecking the connector. That was a good time. Alright, so the one end of these is rough. The other one's relatively flat. If you're going to do this, put the flat ends next to each other. The rough ends might push each other away and cause a problem. So this is the way these should go together. Oh, just the right number of pins too. If I was short, I would leave them off of this end up here because obviously I don't use those pins. So let's go ahead and solder this in. Pi out of the way. Yeah, that's not going to get burned. Who hasn't done that before, right? Alright, so we got some solder here. Well, that must be a ground pin. It's taking a little while to heat up. Thermal relief in there. Let me start the other one. Before I worry about aligning them up straight, that one goes right in. Yeah, okay. Boy, they look pretty good. Sometimes you can just put a connector on there to hold them. The problem is I don't like to risk melting something while it's in there, which could easily happen. This is really bothering me. There it goes. I didn't have enough mechanical contact, I think, with the pad. I don't think this is a 4-layer board. It's acting like a 4-layer board with internal connections. I don't usually put thermal relief on the inside layers of my boards, which makes these sometimes really hard to solder. If you ever if you use one of my designs and you find it just impossible to solder the pins in that are connected to an internal power plane, that's going to be why you need to just keep the iron on the pad a little longer. You get a little more mechanical contact with it, with the pad and that annular ring on there, and it should be okay. Worst case scenario, you can always go back to the power plane and add annular or thermal reliefs. The reason I don't put them on there is because quite often you get areas of the board with a lot of vias next to near each other, and if you put relief in there, the spokes quite often end up like getting to the point where like the filled areas and stuff don't completely fill anymore, and that's much worse in my opinion than a little bit of frustration getting something heated up. But sometimes just a little bit of... It's shocking how much heat you need sometimes to get over the heat sink. A little bit of copper contact will have a little difference, I should say, in copper contact. That looks okay. A little bit sloppy. It's got a big old booger on there. Don't want anything with a little metal tentacle reaching out. That should be fine. Okay. Now we have pins. This back on and make sure you got it on straight because I don't have shrouds on there. Make sure there's no pin sticking out, right? Okay. Make sure this doesn't tear off all these little sensitive wires here. Now, these two dinguses can go on to there if I knew which was which. I suppose I could put on one and see if there's any data and move it if it's not. Or I could pretend like I am a professional, which I sort of am not these days. More of a hobbyist, you know. Okay. All right. And look at the manual. That's where I was going with that thought. Okay. Manual me. I thought I had that handy. Oh, where is it? There it be. Alrighty. Well, what do we got? I got a 340C, but a B and a C have the same pinout. So this is still valid. 2 is transmit, 3 is receive. And I always get a kick out of when people call transmit the thing that transmits to me. Last time I checked, that was receive. So, it is interesting. I don't know which way to read this. All right, yeah, transmit really has data coming out, and that is on this pin. So that would be receive over here. If I can figure out which pin it goes on, it goes right in there, right? Yes. And in theory, that should go there then, by process of elimination. Really loose and flimsy. These are probably pretty crappy little cables. I got like a huge number of them for like $2, so I'm not gonna claim that they gypped me. Come on, focus. Here we go. A little better. Alrighty, now we're in here. We got this hooked up to our CH340. We're all ready to go. No screwdrivers or tinfoil bags lying in here. Ho-ho wrappers. or anything like that. Okay. We'll worry about that reset pin later. Where's my plug? There she blows. If I reset this thing, it should be sending data at breakneck speed. Alrighty. Now I'm on my desktop. There be garbage. What do we hit? Control A, Z. Then we hit, these are my soldering glasses. I can't see the screen. Hello. There we go. Ding, P. What did I say? 119.2? Right there. Please be sending threes. I see a 3, but it's not in auto line wrap mode. I see W. Oh, yeah. We have 3s. Hey! Let's throw together a little proogie that prints something other than 3. And then make the wild leap to getting the whole FPGA. I mean, really, once we get... well, let me just throw that over there. Once we get the console, we should be in good shape. I hear a bunch of noise. That would be the heater fan in the attic, which gets to the point where it's like howling. I can see my compressor is taking it out, but if it kicks into high gear, you may hear it. That's what that sound will be when that happens. Alrighty, we're in here. Going over there. FPGA. We're not going to Progi. ASCII. As opposed to the EBCDIC program. This is truly awesome. Okay. Well, that least significant bit must have been the extra parity, or the stop bit. Okay. What are we going to do? Let's print a message. We can, boy, we should, you know what we really should do is read input data. We know all this stuff works. Let's say cin. And then a return there. So, what we want to ultimately do is make these compatible with the SIO routines. Once they are, we can just use them and compile CPM, and the serial port will go. Then we'll have to code up the bit banger stuff. I honestly think the whole thing might boot. Although I've never tested the SD card on the FPGA board. As long as that is okay. Yeah, as long as I soldered it in all right, right? Okay, so I don't care about the CH340 anymore. Woink! Let's go figure out how to make it go the other way around. The reality is we can just write and let her fly, but we need to wait until it's ready, else we will throw too much data on the ground. Mr. ASCII 115. It has stuff with UARTs. So we need to read the same status rig, like right here, right there. So we're probably reading until that guy's on, and then we return a byte. What we need to do is wait until this guy goes on, and then write a byte. Right? So we're doing this, we check, ooh. Oh, I got it backwards. Yes, we're transmitting right now. Yes. So we end it with a 2, which checks that bit. We need to wait until this one is ready, and then we can write to it. So we do the same basic thing up, basically the same exact part up here. We can play the same games and waste stack. So let's go ahead and just do this whole thing the same way. So C8, you know, I'm gonna, first of all, whatever. What do we got? 1, 2, 3, 4, 5, 6, 7, 8, 9 lines. C in empty. And then he'll go to C. Yeah, that's always fun when you... that one will jump up here. Good luck figuring that out in a million lines of code. Tedro. We need to read instead of write. This is going to be the exact same instruction. We're going to end it with a aux80 for the most significant bitsicle for those of you at home. That would be the same thing if you're not following along. And then down here, I don't want to ouch. I want to in. So it'll look something like this. In fact, if I input the accumulator, I can just use the same code. All right, and I'm not going to read stat O. I'm going to read the read data 0. There's a TD 0. There must be an RD 0. RD 0. Data register. Red row. Red row. Port 8. Reading them up from the old red row. Oops, there we go. And that was on port 8. Okay, now no extra returns. All right. Oh, does that look good? Push AF, spin around, pop AF. Oh, we don't need to save AF at all because he saved it because he was going to write it out. Spin until that bit is on. When it is on, load that into the accumulator and return. Okie dokie, with an artichoke. Now is when we have to concern ourselves with that whole stalled overrun problem. I guess we can just call it, read it, and then just print it back out or something like that. Just so that we know what we're doing, what I'm going to do is I am going to call... What am I going to do? First of all, this doesn't really matter. I'm going to call... this is going... No. Call cin. And I'm going to out it twice. So every time I hit a key, it should come back twice. Assuming this works correctly. It leaves it in the accumulator. If this one runs here and it writes it out, it doesn't wreck it, which is what I wanted to see. And then when it comes around the loop, I can call this twice, and it'll work. Why don't we do 3 to make it really, 1, 2, anybody can do 2. When you go on to 3, whoa, that's a whole nother ball game there. All right, so watch what happens when I reprogram the FPGA. While the CPU is actually still running, it's going to crash. It might start up again. Okay, there we go. All right, now it was spewing garbage, and then I hit the reset button, and it's not spewing garbage anymore. So if I hit 1, it's spewing garbage. 2, tray. Okay, so it did wait until it had a character when it went to cin, and when it I don't know why it stayed spewing. Maybe when I wrote to stat 0, it caused it to do something weird. I don't know. All right, I just hit reset. Interestingly, I did hit 1, 2, 3 earlier. Let's hit 0. I see 3 zeros. I see 3 ones. A, B, C, D, E, F, G. Carriage return. Line feed, line feed, line feed. P, P, O, O, I, U. I can't believe it. It only took how many hours? Yeah, yes, of course. If I had the right clock, that guy's code would have worked fine. But I did not. We all learned something today. I did, anyway. I don't know about you, but I did. All right, so, okay. We have achieved console. Now, you know what I'm going to do is save this, because it's at full engineering rate, that would have cost somebody a lot of money. Let's take a checkpoint. Add. Git commit. ASCII test program. Good enough. ASCII. ASCVI. No, that would be something else, okay? Push that baby up to the GitHub. All right. Now we need to make the quantum leap of getting, doing something with the retro code. I'm going to just hack the crap out of it in place. When I'm done, maybe I'll untangle it. I don't know if I want to just add, like, oh, an alternate support for a different board. And by the way, all I should need to do is create a new directory for a different set of libraries. In fact, there should be 3 library directories. There should be a library directory for the retro, a library directory for the nouveau, and a regular library that's agnostic. If you go into the library now and you remember what all this stuff does, the put S, SD card, and SPI to some degree don't care. SPI doesn't care because it just gets the addresses and the bit positions out of this file here. And put S is just a bunch of formatting things that call the console put S routines, console transmit character, and so on. So this thing is going to be portable. Not that we care about 20 lines of code. They could probably be done more efficiently. There's another video recording in itself, but you know what I mean. So, I don't know. Should we hack in place or not? Let's hack. Let's keep it to the side. Let's make dir a lib. What is this thing? I could call it the nouveau. Like that. Yeah, that's fine. Now, in here, what I'm going to do, when this thing assembles, what happens is, when you say, I want to include this library, the put S or something, what it does it as a path, and it says, look in this directory, and go get it out of there. I believe, everything that does this always allows you to put more than one thing in there. It says, look here first. If it's not in there, look at the next one, and so on. So what I can do is I can copy something like SIO to here, and copy, well, the IO, because I'm going to need to change the address numbers. Lib IO. Copy lib memory. Send it here. So we can start with these. All right. First things, what the heck is in memory anyway? I suspect this doesn't matter to me at all. No. Well, it does, but not really. This we don't need to worry about because we're going to use the same values in the retro. That's part of the stuff that I don't think is going to make any difference. Okay, let's go to I/O. This will make a difference. Now, I'm not going to have a printer port, and the SIO stuff is all going to go away. We're not going to have any CTC stuff. We're not going to... yeah, we may need to do that until we get the MMU working. And then we're going to have these bit positions for the SD card. I'm going to remove these even though we're not going to use them, all right? All the low bank address bits and the printer junk. We're not going to have that. We could hook the user thingy up to the push button on the board. Yeah. No. Minimal, come on. We wasted 2 hours on a freaking UART. The printer strobe, don't care about that either. By removing all this stuff, any code that tries to compile to it will give me an error. So this isn't Retro Rev 3. This is the Nouveau. And it is currently 2024. Wow. We're moving, people. Based on the original schedule, this would be my senior year. If it was 40 years ago, that is. All right, so those things we're going to need to make work somehow. I can even make them be the same bits. It doesn't matter when we're writing the FPGA code. I'll just make sure they match. And the input and the output port, these are going to need different port addresses. And honestly, I don't remember how that works. We're going to probably have to look a little more and digging through the manual to figure out how I/O works for off-chip peripherals. I suspect that there's a range of addresses. We know that by default, the addresses of these, when the thing boots up, these register addresses in here, if you read through this, or I don't know in this manual, it's certainly in the, yeah, it'll be in here as well. There's a way to move these around. So you can say, oh, I want all the on-chip peripherals to be in some range of addresses, and by default they start at 0. And I'm going to leave it that way. I know there's so many of them. My point is that the off-chip peripherals would have to have different range. Certainly can't have the exact same address. So what I can do is I can move them over to like F0, F1, and assume that is far enough away from 0 to give us plenty of space, get us out of the range of addresses that are mapped inside of the chip. And this one here, we can make this one BF. E. I don't want to use FF because FF is, if you generated an I/O cycle and didn't give it any address at all and it was floating, it would look like FF. So, the best not to use that unless you really have to. Especially when you're screwing around with something that you don't really understand and don't even recall if you turned on any pull-ups or not on the bus. Anyway, so let's not tempt fate on that one. Those are just bits. Okay. It might even be best to leave them in those positions because of the way the code works. As I recall, we did something. I remember thinking out loud that if this was in a different place, it would do something differently and blah, blah, blah. So who cares? And I don't want to go back and revisit the SD bit banging code, although it wouldn't be the worst thing. I'm going to rewrite this and create a hardware assist mechanism with a shift register in the FPGA and let it run fast enough that an INIR instruction would be able to run continuously at full speed while the SD card clocks 8 bits and then returns 1 byte at a time while the CPU thinks it's running it as, it's going at the full instruction speed with no wait states or anything. That would be cool, and that's what we're going to do. But on day one, let's just make this go the way it is. I've had enough fun with that UART. Okay, now let's go to Mr. SIO.asm. Now, in here, Yeah, that's actually still true down there. Drivers for the SIO. For the Z8S180 ASCI. Okay. Now, these are called in various routines all over the BIOS. So, what we need to do is make sure that things with the same name still work. Now, I thought I converted everything over to console this and console that for this kind of very purpose. And there's some initialization. B, we don't use SIOB on the retro. So what happens is I think I can just delete all the SIOB routines. I can probably get rid of all the SIOA stuff. Even though it's called in here. We'll have to clean all that up. SIOB, transmit, get all that out of there. All that's internal and garbage anyway. That has to do with the SIOA in it and the B in it. I'm going to change this thing to be like console init. Okay, so there's SIOB RX ready. We don't care about SIOB. SIOB text ready. A text ready. Alrighty. Now, I'm going to add a context ready. I don't know if the BIOS uses a context ready. They added that as a later call in CPM, if I recall correctly, because it's useful to know before you sit there waiting indefinitely to talk to the console. We don't care about any of this. We're going to write our own init routine, which we just debugged. Put it in here. We copy that into there. And we just did the text and rex routines. And the ready status is part of the text and rex things that we just did as well. Okay. So let me get another terminal, because, you need to have 20 of these things. Otherwise, you can't. How can you get any work done? Tell me what are you doing up here? Steal it out of here. Now we got. What am I going to actually do here? When I guess I could assemble this into a binary over here for the CPM. And that bin file, I can either copy it into here, or this can reach over and grab it. I mean, right at this point, I'm just hacking anyway. It just needs to be not so critically error prone. So catrom.asm. So these are the routines we need. There's the init code. All right. Well, okay. Oh, we also need to do this other stuff. In the boot flash, we'll do that. And then, so here, I'll add this to my I/O routines. In here. Well, let's not litter the global namespace with that junk. Why don't we also rename... Well, the problem with SIO now is that if I rename the SIO file and somebody includes it, they'll get the other one. I know. Move SIO.asm to console.asm, which I should have called it that in the first place. Now, if I create an empty file called SIO.asm, that'll force anybody that tries to include it with this in the path before the other one, which is where we're at right now. When I go to do the compile, it will get an empty file so that it will at least fail or it will not use the wrong data. That's the critical thing, right? So this is con. I'm going to just delete this SIOA crap out of here. And then here's my initializations here. Anyway, so I don't want to put this in the global IO file. I don't think, maybe. I don't know. I don't know why I lose sleep over this stupid, simple crap. I would rather not. That's all. Okay, so this is going to be local well, actually, this file gets included, doesn't it? Due to the way that this assembler is being used. We have to put dots on there for this, okay. We'll keep the credit where credit is due, or blame, as the case can be at times. So, the init code. I stole it from there. Mod's my fault. All right. And I'll leave it as a test of the reader to figure out what was modified by moi if they didn't watch the video. Okay, I'm going to just leave that alone. It does appear to work, however it works, right? Then we will put that in the firmware file. That's what I just copied. There's the loopaja boopaja. Okay, here we go. Here we go. Now, that's the full transmit character routine, and then here's the readies in the ready room. Transmit ready. I don't need to even care about that. A equals 0. We got to keep that. Remember what the rules are. Set to non-zero if it's ready. Return non-zero. Oh, I remember this. There was something. I added this to the doc because I took advantage of that. Clobbers AF. So I added that as a feature. So let's not make that broken. Let's make sure that stays true. Check if it's empty. So what I'm going to do, I'm going to read it. There you go. It returns non-zero if the transmitter is ready. So I can simply do this, and that is true. Whoops. What happens? If A is 0, it's not empty. Check empty. If A is 0, what am I doing? I'm waiting for it to be to become empty. So the transmitter is ready when this is not 0. And that is still a true statement. If I do this and I get a 0 in here, that means it is not ready, which is why this code stays looping. Once it falls out, it is ready. Okay, so that is, I believe, correct as stated. Return non-zero if A receive is in fact ready. Now, I don't know if that means it has to be a 1 or a 0. Let's go back and read the comment in the original code. What did I do wrong? View. Come on, idiot. Okay, so this one ended with 4, and if it was non-zero, it would be 4. So this one will, if it's non-zero, and the new one, it'll be a 2. So no big deal. This one happens to be a 0 or a 1 due to the bit position where the ready bit was. So I'll just go ahead and put... I'll have to put a little bit extra code in there, or at least eventually we'll have to look around to find out if I care that that is in fact the case anymore. Return non-zero if it is ready. So that it's going to be the same sort of thing. which we did down here for the input. That's receiving, yes. So that one will do what? It'll actually set the high bit if it is I wish I could remember who cared about this. It was SIOA-RX ready. Grep minus R. SIOA-RX ready. It's all references everywhere. The only place they ever uses it is in itself. It is not used anywhere else. So I'm going to change the dock and not do this anymore. That might actually have it might have been something at one point. I do remember talking about that. Non-zero if the RX, if the console is ready, and Z with A equals 0 if it's not ready. That is correct. That is true. Return non-zero if console UART is ready. That's all I'm going to guarantee, the non-zero status. And it will be Z with A is 0 if it is not ready. That is true. Okay, yeah, in that code. This one will do this, that will do that. Fine, and it's done. So all I got to do now is say call ready. And that had to do with this right in here. So I didn't have to compare A after I got back. So it goes around this SIOTX care back to here. So I can just go back now to context character, get this garbage out of the namespace. Then I load A with C, because remember, this is for the BIOS. It puts the character in C that's to be printed. I move it into A. Now I need to actually write it. And the code to actually write the character is, what does it do? It does this. Put it in A. Actually, well, if I look up the instruction, I should be able to output the C register instead of the A. But let's just leave this the way it is so I don't make any more mistakes. That would just simply mean I change the value in here. The 39 means write out the A register. Different bits would be the C. All right, so that's for sending. Now for receiving, we'll do a very similar thing. Call conrex ready. We didn't do that up here. And if it's 0, keep waiting. It becomes non-zero. Yes. Now we say wait until we're the receiver's ready, and then go get the value from the receiver buffer. Put it in the accumulator. And then return it. I don't know what that comment means. I'm going to leave that spaced out a little bit here. Okay. I think we have a console. Now, I don't know if the BIOS was uniformly converted over to always use con this and con that for everything. But I think we're in the ballpark here. This is actually going to be really cool. Okay, those are close. bootage. Alrighty. Where's the libraries come from? Right there. ASM flags. Screen capture's a little off. So when you say /lib, I'll bet I can say /lib NOUBEAU and lib like that. And it'll scan them both. So let's see what happens here. Woohoo! We're adding. Alright. Now. I'm not going to do the all I'm going to do right now is see if I can load this software and run it. So I'm going to say if 0, right? Is that I can't even remember how to use the wonky preprocessor. I'm not used to not having to put a pound in front of it. Is it end if? There's probably some in the file somewhere. There you go. Yeah, it's if and end if. So it's going to wake up at 0. It's going to load a temporary stack. It's going to init the console. So I'm going to say so what we could do to make this more portable is you just put this code as you see it into an include file for like a lib retro, and it'll include, either the retro one or the nouveau one, depending on how the make file sets up the include path, which would be cool. And I'll, maybe someday do all that if all this works swimmingly, as they say. So let's call con init, which I believe we just wrote. Where are we at? I am in the middle of FPGA land over there. Do I have another terminal? It's running it's running the Minicom. CPM. Where are we at? What am I doing? We're gonna go to live something or other at con. Okay. Right, yeah, that's the one. Okay, and then we can just go on our merry way. Puts, yabba dabba doo. Call I put S, boot SD. Let's comment that out because we need to set up the Verilog to make the ports map to the SD card bits. And what else do we need to do? We could load up I could just boot up the Retro's SD card as it is without even doing anything to it. It'll crash though because it'll try to start up it'll reinitialize the SIO, and something doesn't exist, it'll crash in there. But it would be interesting to see if it can do anything at all. Maybe I'll put a little hello world file on an SD card. I'll consider that a very great success. We can make that full leap. And once this goes, so the boot SD. I think that's just going to all just work once I map those bits. Okay, so then there's includes down here somewhere. There we go. So the IO and the CTC. There's no SIO? SIO, there we go. Okay. These need to be redone. We don't have a CTC anymore. The only reason this was in there is to initialize it in case we wanted to use a different baud rate. The SPI has real hardware I.O. in it that will probably fail. Actually, it won't. We left those defines in there. They're wrong, which is why this won't run if we try to actually boot the thing. But it will, it should assemble. Provided that we don't trespass into that code. And up here it does the I.O., it does the memory. It does memory so that it knows what these values are. I think that's okay. Connet, do this, do that. All it's going to do is print stuff. Which, okay. It cannot find context care. Line 476 of God knows what. Oh, it can't find con ASM. Okay, here we go. Include new line. Is that what I called it? Yeah, it might help if I named it right. Nouveau. Oh. LIB. Not bad. Okay, it can't resolve these because when I put a dot in front of it, that actually becomes part of the name. So that is fully understandable. Where is this? Where am I at in this window over here? I'm right where I want to be. Con ASM. So all these things now, when I use them down here, I have to have dots in front of them. This is a comment, but it will work when I use the right assembler. So we'll continue the charade. Well, that we will get back to this someday. That is not right. We need to get rid of that. Okay. That would have become very confusing. It could have been innocuous for all we know. It could have just been sending crap to some random place. All right, let's see. Well, let's see. It assembled. Of course it's going to work. There's no errors. Okay. All right, what are we going to do? We're going to go over to... I guess we're going to just hack this. Why don't we make dear this and copy the ASCII stuff into that. And the RAM ASM file, how does that work? Does this just simply say ram.bin or something in here? ROM hex, here we go. This is going to be ugly. If we go to ... / this and just grab it from over there. This is so bad. All right. That file. Ooh, we don't have a bin. We need a hex file. That was the thing. Yeah. Okay. So we need to make a hex file. Oh, that'll be very convenient. Very convenient indeed. Okay, we'll leave this the way it was. In fact, we just undo our way back to the beginning. And in the make file, we will make the ROM hex. You see, this thing does all that stuff. No, that's the dependency. Where's the... Here you go. Make a binary out of a hex file. And he runs hex dump, blah, blah, blah. The problem is, if I list the binary is way over here, it'll put the hex file way over there too. What I want to do is just go steal this stupid thing. He's dependent on ROM hex. So what I'm going to do is I'm going to say ROM hex is dependent on well, I'll just put a hard-coded crap rule in here. I don't want to waste all my day on this. There we go. Copy this slash this guy here to here. Then wait a minute. Hex to bin. This is the bin. In order to get a ROM bin file, we're going to go steal it from there, and we're going to not only do that, we're going to call it rom.bin. Then this should be able to convert it to a hex file. So when he says, I want a rom.hex, and he goes, I can make one out of a bin, but I ain't got no bin, so I got to, but I can make a bin if I do this. Provided that I'm making rom.bin, which is what should work. Let's see what happens here. That's not what I wanted to do. Make mine is actually, now that it's done, it did do the copy. Yeah, make clean. There we go. Make cannot stat. Okay, you're right, it can't. I need to go up one more. Yeah, ba-da-ba-doo. There it goes. Boy. ROM.asm is still sitting here. And it could have, oh man, make clean. Make rom.hex. What's it going to do? Okay, it did not assemble this. I should just remove it. This is a copy from the one that is in the ASCII directory anyway. Oh, I know. I'll move it to that. There you go. Just so it can't accidentally somehow get used, which is the goal. Alrighty. So if I make probe this, if it prints anything at all, then we're making progress. Okay. I hit reset. That is where I wanted to be before lunch, people. Oh my gosh. You know, I'm still pretty impressed. This is insanely awesome. Now, how do we do boot up all of CPM? Well, it turns out that because we've already done an insanely huge amount of work in that area already, I think the rest of that is Verilog. I'm pretty sure that's all we got left to get the SD card going, and then as long as you only need a console, which is 99% of what CPM uses. Let's see here. Oh, CPM will crap out if we don't do this as well. And by that I mean if we have to get this out of the way, because CPM doesn't want to have ROM at address 0. Because remember the CPU is accessing memory inside the FPGA for the first 4K of the memory, and then it can't write, it can't store anything in there. It won't work. So we have to make sure this can go. We don't care about the output cache really anymore, because we can actually implement a readable register in the FPGA if we wanted to. We don't really care. Because all we're going to do is what? Bank 14, idle the SD card, and those other, yes, and then output that. Okay, so we don't have RAM banks right now, so we're not going to worry about that, but we do need to do these other things. And then we need to shut off the flash. We input to do that. Okay, and then, all right, this is going to go. Only come down in here. I mean, as long as the SPI driver works, the whole thing will go. That is so cool. This will be truly awesome if that happens. Now, the next thing that's broken will be what? The live directories from make files. How about */make? Because we have to make sure that everything, in the hello. Oh, look, there's a hello program. This is the retro BIOS, and here's some tests. I totally forgot about these. These probably. Oh my. Well, I don't want to have to relearn all this. Well, why not? Let's see what happens in here. What does it do? I forget. Do this, do that. Suitable executable program to use with this is the hello. So what this is going to do is exactly what we want. And by that I mean, we don't have to figure out how to recompile all of the retro BIOS, because we got to remove the printer and all that other stuff. This is the thing. Once this goes, we're golden. And the SPI test. Oh, I don't know if this has its own SPI code or if it uses the library. What does it do? It does like the boot ROM. This is the same thing as a boot ROM. It's probably, yeah, it is. It doesn't surprise me at all. This is probably because what it's doing is it's going to read the hello program off the disk and run it. What does this one do? All of these probably do that. I don't need any of this, actually. I just need to put the hello program on the SD card and run it. Yeah, that's not a big deal. These are my early test programs that became the bootloader. That's awesome. And anybody can write any old hello program. So hello is probably going to, it's using iPuts and, oh, look at you. So we got SIO and CTC, but I bet it doesn't need it. How does it initialize the, note the bootloader should have already initialized. That's awesome. The console. Oops, etc. Therefore, we can just write to them here without initializing. Don't forget the null terminator, blah, blah, blah. Now, we certainly don't need that. And we can do this because, actually, you don't need that either. This guy does not call it. Oh, he might need to have it in here so that putS can compile. All right, because this probably calls like SIO routines and stuff, as I'm sure does hex dump. So we need to make sure that the hex dump and putS got updated to use con instead of like SIOA. So the hex dump should be in here somewhere. So when he prints, what does he do? See, he has all that con. which is exactly what he should have. Beautiful. Now I can just, I'm done. Oh, yeah, that's hex dump. What about put S? So you give them logical names. Or more accurately, I should look for SIO. SIO anything. That's great. Thank you. SIO from star.asm. It should only happen in the SIO file. SD card is version. What about NH? Oh, that's a whole other thing that I was dabbling with. Memory. IO, ASM, we're going to use the other one, so that doesn't even get used. These are just, oh, beautiful. I love you. All right, so they don't need any of that junk at all. Grep SIO.asm from these files. So nobody actually, in other words, they don't have their own includes SIO.asm. So that's why you had to include, whatever you need in here, even if you don't call it directly. So I'm going to do this. This should actually compile if I put the right thing in the libraries. So down the road, when this is all done, what I'll do is I'll put these ASM flags in an include file for the make. So it'll say include ... make rules or something. You've seen me do that and other things on my channel. That way I can configure in one place whether I want to link in the lib nouveau library before the regular library or the lib retro library before the common stuff. And when I unravel that, then I'll have both of these will be able to run using the same build scripts and things. Okay, so now I have a hello program that if I was to put it on an SD card, which I assume I documented how to do in here, or I'll have to watch my own videos. Oh, that's so upsetting. When I Google something and I get my own video as the answer, it's very embarrassing. It's even more embarrassing when I get my own video and I don't have the answer in there. That's shameful, bad John. Use this to save a program out of the partition. Put in executing firmware ASM boot ROM code in there. So that's how you put it on the drive. Now what this is going to do is write this onto the first partition. Yeah, not the boot, not, the MBR. This goes into SDA1 where, like the retro BIOS would normally go. Use this command to save the program on the raw drive, overwriting the MBR, suitable for loading. That will wipe out the MBR. Suitable for loading and using the SD test ASM. So SD test ASM, okay, is the program, as you recall, that reads the first physical block off the SD card and expects a program in there. That was what I did before we used the MBR and all that other fun stuff. Once I booted off the MBR, you use the regular bootloader up here and you store it in partition 1. Notice this thing is SDA and that's SDA1. So if I write this into SDA1, what I'm doing is I'm clobbering, if I have an SD card with CPM on it, I'm blowing away the CPM partition, but I am not blowing away the MBR. So this is the one I want to use if I'm going to use the firmware, the boot firmware, that I'm playing with right now. So that's how we program the SD card. Once I can find one, then I can boot that sucker. Does this even make sense? Let's have a look-see at the list. Make sure it is sane-ish. Okay, this is wrong because it's getting the SIO crap. So that first line of code is wrong. That means my load library path is wrong. What did it use for the SD? Well, this is the right one here. Oh, does it have? It is an IO.asm. It does not have a memory.asm. Is that in memory? That's IO. Yeah, this should be IO.asm. How come it got the wrong one? There's memory.asm. Well, here's it copying itself. What's it doing? Hello, waste time, go back and print again. Yes, and we never get here. Okay, that's what it's supposed to do, and then it loads up these libraries. So how did it get the wrong IO.asm? It's right there. Live Nouveau. Oh, is that? Wow. It could be that this doesn't do the right thing. I mean, this assembler has got a lot of other problems with it as well, as we know. Wow. Why does that not? I don't need this. I don't need this crap. IO.asm. We can also be a total pig and go like this. That might work a little bit better. And now you can see that it got the right one. Oh, did I not? Or I'm a dingus and didn't notice that there were semicolons in front of all these in the last build. Let's see here. It may be that I just didn't look right closely. No. That is like really, it's like weirdo. I'm missing something. Yes. I'm copying it because I do not want to type that. Maybe there's a bad character in there. Now that is definitely just, I don't know. The UART was enough fiasco for one day. They know that the memory is going to come from there anyway. You know, it is possible that some tool decided that it would look here first and then it would look there. It is possible. Because the only things that I'm grabbing right now is con. And I don't directly load SIO, and even if I did, it should get this, but, you know, it could go either way. But IO is in both directories. Con is, my point is, there is no con in lib, so no matter what happens, as long as it looks in here, eventually it'll find it there. So maybe this is backwards, which is stupid. You do something like an assembler, it should be the same as all the other ones that have come before you. Do not redefine this. This is stupid. I'm like, just, I'm going to barf. That's what's happening. What am I looking at? Hello here. Bye. Hello. And I'm going to put the original one back in there now. Make world less. You suck! Holy mother! there's another nail in the chest of the guy that designed. Oh, this is so dumb. Oh my gosh. Let's make sure that we don't do anything like anybody else. This is backwards. Oh my gosh. What's going on over there? All my yelling stirred up the dogs. There's a dog pawing at the door. Are you okay in there? No, I'm not. I had a vomit. I went vomitosis. Holy crap. It just goes to show, when you get old and how many times somebody does something incredibly stupid to annoy you. The fact that I could figure that out. Who else, huh? Oh my gosh. If you're still watching this video, I love to hear your stories. What is the best ineptitude? What I call a sighting. Of what I won't say on YouTube, but we call that a sighting in my office. There's a sighting, all right. It goes up on the whiteboard. Today's sightings include, usually it's somebody in the postal services who cannot find our office in a building that has a gigantic number on the front of it. And by the way, it's the first one when you pull in the parking lot. Where's building 15? Well, it'd be the one with a 15 on it. Best story there is I got a call, and you get like, Amazon, a driver needs assistance. Will you accept their call? And they say yes. Yeah, you can actually see I missed something here. That'd be all that is the noise for the printer stuff. Anyway, they go, will you take their call to help them deliver your packaging? Yeah, sure, fine. Can't find your office. I look out the front window of my office, and I see a car idling out there, and there's a person on the phone. I go, tap your brakes, and then brake lights go on. I go, in your rearview mirror, what do you see? They were literally, without exaggeration, no more than 10, 20 yards from the front door of my office, and no. You wonder if you ever have a problem getting your packages from Amazon when they use the local drivers. Oh, these are not Rhodes Scholars. Look, I'm not a genius, but have you been in an office park before? Just unreal. Number of times that happens in a given day is astounding in that particular office park. It really is amazing. Okay, what am I doing here? The problem with this now is that because we removed all the printer stuff, that's gone. Yes. Yeah, but do. Printer strubage. We don't even care. It'll just write bits into the FPGA that it will throw them away. Perfect. Okay, now we know how the include path works on this hideous thing. Clearn! Make world. Come on. I can't think and type at the same time. All right, so that is good. Well, the reason it worked... Whoa. Why did it work before? It worked before because IO.ASM does not have anything in it that is critical to the ASCII. That's why it worked before. Remember, I made them local variables inside the console, the con ASM file that is in lib nouveau. So that's why it assembled either way, whether it had the right one of this or not. So that's all good. All right. That's all good. This is so close, I can't believe it. Oh my gosh, let's see here. I have to roll a new file. I'll be right back. And we're back. I had to reset the recording so the video files won't get too big. All right, here we go. In here. Now let's see if I can just guess my way through this without doing any real testing. So that's worked so well today. So far. I need to map the SD card into the FPGA universe. The pins here? No. Jerkwad. Alright. What does he actually do? I need an I.O. port. I have yet to do anything in the FPGA related to I.O. I've only dealt with memory, and that's what's going on here. When the CE and WE are both active, low, and the address is this, I generate a signal that says, I've got a write enable to this address. And that's a lot like, that's basically the same exact thing I'm doing over here in Mr. Retro. Oops. Oh, that's not the Retro, that's the Nouveau. I need the old Vo. There it is. That's what's going on with this bugger right there. So I need to do this. Hey, how hard can it be? I get these address lines, I get these, and we're done. Sort of. What we don't know, what I don't know, is what happens when the I.O. goes off the chip. I'm going to assume that by default it somehow just works, and that I don't have to actually configure it. I suspect that is the case, but I don't know. Well, it'll be easy enough to just try it and see what happens. So I can generate a signal. Let's generate some down here. Let's generate a wire called, well, we can actually call it, what did I call it in here? I can call it IO-REC, whatever. But you can't use those ports because those are on the chip, right? So I'm going to just generate, that's what I'll do. I'll generate an IO-REC something. What did I say? It'll be like F1, F2, and things like that. IO-REC F1. IO-REC F2, and these will be active high because inside here I don't want all this stupidity of remembering what's high and what's low and all the other crap. No real value. There could be if you had a chip that had wired AND gates, wired OR gates, and stuff like that, but we don't, and I assume that the synthesis tools will do the right thing and invert it all in order to optimize the placement on the chip anyway. So we need to make sure that we have an address, an M1, and IO-REC are active at the same time. M1 is high, that's right. Because if M1 is low and IO-REC is low at the same time, that's an interrupt acknowledge. We need to make sure M1 is high and IO-REC is low, right? That's what we need. Why don't we find the manual? It has all the pretty pictures in it. Home ski. There's a timing diagram. Standby. I.O. Standby features. Well, we can look at the internal. I'll bet anywhere it'll say something in here. These occupy 64, including this. Registers are internal are these and that. And see where it says I/O relocation? That's what I'm talking about. So you can move them, but if you by default they show up at 0. To avoid address conflicts with external. Internal can be put anywhere you want within the bottom 256 bytes of the 64K I/O address space. This then has all 16 bits. If you use the in and out instructions, they use all 16 bits. But if you use the old Z80 ones, I think they're the same. Therefore, it should work. That'll be another test. That's why they have that special in 0, out 0 jazz on the S180 chip. So there's this control register that says, here, where do you want me to put my internal things? And if it's 00, that means it's in the bottom, what they say, 64 bytes of the I.O. space. That's why I guessed and put mine at F something. I don't know what I.O. stoop is. Stop mode, normal, I.O. operation resumes. Stop mode is enabled when that's set to 1. Well, let's not set it to 1, because I don't know what that mode is. I love it. They tell you how to figure out. Yeah, let's burn a page on that. Okay, internal mapping, I/O. Oh, here we go. This talks about which instructions to use. We might want to do a quick recap. Internal guys are in here. 16-bit I/O, because the Z80 has an 8-bit I/O. Thus, to access the internal ones, you must have a 0 in the higher order bits. Conventional instructions. Place garbage on the higher order 8 bits. It's not garbage, it's known, and people take advantage of it, but it was an accident of coincidence and became a feature of the Z80. We all know that story. Okay, for efficient internal access, a number of new instructions have been added to force the higher to 8 bits to be 0. These are those which you have seen me encoding these by hand. When writing an internal thing, what? Yes. The same I/O write occurs on the external bus at the same time. However, the duplicate write cycle exhibits internal cycle timing. Therefore, the wait and wait state generator are ignored. Similarly, internal I/O read cycles will cause a duplicate on the bus, however the data is thrown away. Normally, the external I/O should be chosen to avoid overlap. Wouldn't that be a good idea? And here they are by default. Okay. All right, that's great. And if an engineer made this, you'd have at least 4 times as much on one page. And I'll bet that's still not visible on your phone, by the way. So then we just go into all this fun stuff and we start looking at the regs. That's lovely. Timing. Come on, timing. Whoa, I saw a timing diagram go by. There you go. There's your I/O. Interrupt mode. That's interrupt timing, not I/O. Int 0. Interrupt priority crap. No. We looked at some of this before when we were trying to bring up the board from scratch. DMA, garbage, memory map, memory to I/O. Oops. Well, that's for the DMA controller. Now we're... What? Where the heck are the timing diagrams? You stink. Oh. Found it! It comes before. No, I don't even remember what the heck I'm doing. Yes, an I/O cycle. Opcode fetch, blah, blah, blah. With a wait state. Without a wait state. With a side of fries. I/O, there we go. Okay. The I/O address is on there. This simply means no wait states. It adds its own wait state. I/O rec is low. Read is... There you go. I knew there was something else going on. When I/O rec is low and read is low, IO-rec is low and write is low. Okay, why did I do this other one this way? What's CE, by the way? Oh, I might generate that elsewhere in here. CEN. Yes, it is a signal I generate from MREC. And the address is greater than that. Whoa! We have a conflictage. Whoa, that I didn't notice. That's like badness. There's another reason you need to use a local param. That's just dumb. This is why I said this is ass, because they both have to have the same value here. That was like bad. Oh boy, oh boy, oh boy. Fine. So this one says I need the RAM on while it's being written. That's what that logic is. And the RAM is supposed to go on when it has the correct address range, which is supposed to be this. And, you know, if I had any brains, I would make this, fine. Make it into a local param, which is what it should have been anyway. What do we want to call this one? RAM start. The thing about this is that's true until we shut it off. So we're going to have to come up with that toggle bit thing. But that's fine. I think this is correct. Oops. Well, this should still build, or not. Executing stuff. Toke wire. 99, what did I do wrong? Oh, fine. Fine, now we're in the ballpark. Alright, IO-rec for F1 is going to be true, much like this. Now, I generated CE low because I need that for the actual memory chip on the Nouveau board. The CE is connected to this, alright? These are all active low. That's why I did that when I made it low. So IO-rec for F1 is essentially going to have a similar sort of a thing going on here, but it's going to say, it won't be MREC, it will be whatever this says. It'll be IO-rec and oh, I see. What I did is I enabled it for both reading and writing. I didn't care. You just have to not do it wrong in the retro over here. And I remember talking about that as well. Just, doctor, it hurts when I go like that. Well, then don't go like that. Okay, so we might as well do this one more reasonably. We can call this one like write F1 and read F1 and stuff like that. So we can do that. We can call this IO-rec F1, like write F1. One of these is supposed to be the read. I don't remember which. It's in this other directory. I'm all in the FPGA code now. Oops. This /lib nouveau something or other. Yeah, IO bang $/IO.asm. I wanted to have something what? The input's on F0, the output's on F1. So if I say generate a signal that's true, when A is aux, F1. And what is he going to do? That's my input, F0. Everything's backwards. Read from F0, please. Writing to F1. Actually, I could... do I want this, or do I want to just call it GPIO-in? For now, I'm going to leave it the way I wrote it. Okay, this one is going to be... what do I need? If I want to actually, read from F0... IO-rec low, read low. And the address is that. Okay, so IO-rec. Hopefully we have an IO-rec in here. DREC, IO-rec, and read. Okay, IO-rec is low, then that becomes true. And the read is low, then, that would be true. Come on. And the address is exactly equal to that number, then I must be reading from there. And a similar sort of a thing down here, if the address is F1 and I am writing, then that'll be true. So these will allow me to put always blocks in here that when this is on, it will capture the data from the data bus and make it available to the SD card. Now I need to make it available. Now I need to make sure I don't do too much glitching on the SD card, because remember, I bit banged the clock. So if I capture data, I need to have a clock edge to tell me that this is when to do it. So I think what happens is normally there's a hold time on the read data beyond this rising edge here. Well, that's for reading. That's not the one I care about. This is the one. When it's writing, the write data from the CPU should stay on there longer after this goes high, is my point. And in fact, the data sheet should have the actual numbers. As long as it's more than like 1 nano, we're fine. Here's the data sheet over here. There'll be all kinds of timing stuff somewhere. Here we go. IO read, IO write. Well, that's exactly what I want. So this goes down here. You see this address has to hold the right signal. They don't show you the data. What's the point of it? It cluttered up my diagram, so I left the data part out. Opcode, memory write, IO, here we go. This is the one that's got everything. IO rack goes high. Read and write will go high over here. If it's doing, okay, so it's going to look like that. The address goes on here, so there will be some time. See this 11? The 11 is the hold time on the address after this goes high, which is relatively important. And the data, when it's outputting, it's going to be like 27 over here. Should be the hold time on that. So 27 and 11, probably. There's also a 16 in here, measured from, 21 is from, it's this one, it's 16. 16 and 11 are our friends. 16 and 11, please. There we go. Like, don't tell me they cut this table for space. 16. Ooh. Data read hold time. Oh, that means I can take it away right away. That's fine. 11 is the address hold time from this. So that holds it for 5 nanos on the address line after the I/O signals rise. I don't like this data read hold time. I want the data write. How long is data write held after address valid to this? Dang it. I was looking at that was for the writing. They take it away immediate. What? Oh, data out is 27. 16 is when I read it in. That's right. So I can take it away pretty fast. And they're going to hold it hopefully longer for time period 27. Assuming I'm reading all this correctly. Okay, 10 to 5. 5 should be where I'm here. I got 10 nanos. I got forever. That's a 100 megahertz clock. Okay. While we're only running our FPGA at 25, this thing will run at like 200. So the LUTs and stuff, this is not a problem. Our timing will be fine. So when these signals become false on that edge, these are active high, so there'll be a falling edge. When this write has a falling edge, we can take the data that we have seen recently on the bus, and we can latch it as our output value. So, and this is just slob. Always. Now this is. I can say what? If I do this on the negative edge of that signal, yeah, this is kind of bad, but we'll do it anyway. What happens is, when that thing is falling, is when we know we're at the beginning of the hold time for this write cycle. Okay, we're right here, and we know that this data is valid at that time. It's been valid for a while, so if we take it and latch it into a flip-flop inside the FPGA, so we can call this one GPIO out equals the data bus D. Now we also have to be careful. As you just saw, the data bus is bidirectional. We need to make sure that the data bus is in input mode at that time. So what happens is, see where it says D equals either we're sending it stuff from the ROM or it's floating? That's fine, because that's MREC under this thing here is the only time we write to it. The rest of the time it's floating, and when it's floating we can read it. And we do read it because we read it in this logic right here whenever we're writing into the all ones address port. So we don't even need a begin and the end. We're going to do exactly the same thing we're doing there. And I will laugh because this is also somewhat sloppy. This is not synchronous code, but it's fine. It's synchronous in terms of the gates and all that, but it is not synchronized to a global clock and all that fun stuff. So there is me running GPIO out. Now the question is, how does GPIO in work? And that is a whole nother ball game. which is related to this guy up here. Now there's more reasons to send data to the data bus. If he's reading from GPIO in, we do not want to send ROM data to it. We want to send our GPIO in bits, okay, which have to come from the SD card, which have to be these signals. Where's my, here it is. Well, I have to send it the card detect. Actually, I need to send it MISO. I don't think we use the detect in any of the code right now. However, there's no reason I cannot hook those two bits up. So I need to have a way to propagate those in. That should be easy enough. And I need to make sure these are in the right positions when they go out. So I will just create some signals that have the same names. All right. So, well, actually, that's part of this GPIO out. So what does that really mean? The output bits in this port are really going to be assigned to these things that go to the SD card. And these things that go to the SD card need to be ports in my top-level module that I'm hacking. So I need to create a MOSI, a clock, and an SSEL. And hook those up to bits that go to the SD card on my FPGA board. So it turns out I would do that by saying, you know, just put these. I'll make them lowercase because uppercase usually is, people only use those for like macros and stuff. I wouldn't want to mix styles. Okay, SD5. I don't remember why it's SD5. Why did I feel the need of calling everything SD5? SD and SD5. Oh, 5 volts, 3.3. We don't have that problem. These are actually 3.3 now, so that's what that was. These are going to be the ports that I'm adding to module, and then I'm going to connect them up to the SD card in the PCF file. So I'm going to say that equals GPIO out. Same ones that they do here. That's Q0. All right, so that'll be GPIO out 0. This one will equal GPIO out. Clock is 1. And this will be 2. Right? Help if this was not some weird thing going on over there. SSEL clock and MOSI. SSEL clock and MOSI. 2, 1, and 0. 2, 1, and 0. That will give me an output port that will allow the exact same code to work from the SPI library and the retro. These 3 bits for the output. Now I got to map the input for the MOSI or whatever the other direction is. So I need to add these to my. These are actually, what are these? These are outputs. Output wire, and they're single bit values. Get rid of those. Fine. Those, okay, that's it. Now I need one more for the input. What is that? Rank. I need to put this somewhere. MISO. As far as I know, we don't use the detection, but I'll go ahead and hook it up anyway. Now, we need to make sure that the polarity of these are also right. SSEL is active low. I should have put an N after it. Yes, okay. I don't have to do that. Clock and Mosey are as they are, because the SSEL has a bar over it, okay? So the Mosey and det are true, which I think is wrong. If you plug a card in, yes, there's a pull-up resistor. The way this thing works is that when the card goes in, there's this det switch thing here. What happens is the card goes in, it opens this circuit up, and this gets pulled up with a pull-up resistor, which is over here by this. It gets pulled up, okay? And when you put the card out, this switch closes and shorts it to ground. So SD det is as is stated right here. These other ones are all true as well. So meso and det need to give us an eyeball into the data bus. So that means this is going to become more complicated. We can make this have more question marks and more crud, or we can make an always block and just do it in there. Now this is really sloppy. I'm just throwing crap all over the place. We might consider like modules and things, okay? I just want to make it go. And if you sit through this entire video, so do you. D, okay, so here's the deal. D equals Z unless otherwise stated. That's what we're going to do. And then we're going to say if this is true, then we're going to say D equals ROM data. Else, if something else is true, we're going to say D equals, we are going to say the meso det stuff. Alright, what are we going to do? We need to make sure we don't have to redesign the I.O. routine. We could use the old I.O. File as it is. But the reason I took all these other ones out is to make sure that there's no code that's going to access those other names. So I know I didn't assemble it wrong. Like getting the includes out of order. That would be a nightmare to debug that one. So det is on, where am I? They number this one like a bunch of dingbats. Oh, here we go. Det is on 7 and, or 6, meso 7. Det 6. If I do one of these, meso's on 7. Who's on first? I don't know who's on third. 5 tick BX. We don't really care what the other bits are. How about 6? What do you say we put the right number of them in there? That'd be real confusing. How come the det is showing up for the printer status? Okay, so we got what? We have det 6, meso 7. Now, I'm assuming that this one here connects through to there, the O3B, I3B. I'm pretty sure that's the same thing, right? We hope so. So meso should be 7, det 6, and the other ones I don't care. And that's done. Now, when does that true? That's true when Mr. Writing to F1 is true. I'm an IO rec or write cycle on that address. IO rec on that write cycle on that address. Now, I don't recall. We can put it in to be safe. Making sure that M1 is high during an IO cycle was a thing because of the interrupt acknowledgement. Remember, it asserted an IO rec during M1. And I think I'm going to go ahead. It does, it should not hurt anything to say, oh, by the way, make sure that M1N is true. In other words, is not in an M1 cycle. Why is that all upside down? That was because I stole it from somebody calculating Oh, this was going from here, I think. I'll get over it, I suppose. To put all this in the same area, maybe it'll... Well, it doesn't matter. Okay, so where were we? If we want to float it, unless we're in the middle of reading from memory, or we're writing to memory. What? If we're writing, we don't care, for crying out loud. It's not writing, geez. If we're reading, yes, okay, then we're going to send that stuff over from the SD card. Okay, and then this one is writing. Fine, so read up there, writing down here. So we want to make sure that M1 is high. It should be in here, right? M1, yes. Okay, M1, where are we? Down here, yes. M1 is high. IO-rec is low. Read is low. And the address is the one I want. Then this whole thing becomes true. Which is a binary 1. I could also then, to make it more explicit, I can also say 1 else 1 be 0. If you really want to make sure that you truly are sending a 1 and a 0 into a 1-bit wire, you can do that. Okay. And without having to do test cases and everything else, we have to kind of really make sure we do this right. OZ clock and all that from 01 and 2. That was correct. 01 and 2. Okay, all right. Just go for the gold. Why not? All right, so now we have to put these in the PCF to hook them up, which means we got to look up the schematic for the CPU board. Which is up there. In there? No. Of course they're not in there. That would be useful. Alright, set IO. And what are we going to... Oh, we just give them the pin numbers. Mosey. So we can just go like this. Set IO. Oops. And then we will get rid of these commas. And then we'll set them equal to the pin numbers that we want them to be. Which are not in the breakout. We need the schematic for the FPGA board. Which is actually not far from this directory, except I'm on a Pi, and that's not on my desktop, so I don't want to open a PDF browser over there. I can open it from over here. There's a PDF in there, thank you. Go away, come back. Okay, here we go, here we go, here we go. Whoa, that one's a big one. Get it to fit on the screen, please. Okay. Alright, here's the SD card, and you can see the I.O., this, that, and the other thing, but those aren't the pin numbers. We need the pin numbers, which is a little annoying. So, oh boy, so I need I.O. T174. Alright, I may have to open this in KiCad and do a tray. There it goes. It's on pin 117 right there. So that is what? That's SSEL is on 117. Okay, what about Mr. Clock? Clocker is on 191. T191 is on 124. Yeah, I got two Moseys on here. I'm guessing I just copied it twice, I hope. Where's Mr. Mosey? We got a Mosey on over there. Mosey. Is IoT 178. It's just 119. And Mizo. Mizo. 181. Mizo. Is 121. Mr. Card Detect shows up somewhere. 192. IoT 192. On 125. Now, maybe that's right, and maybe it's wrong. One thing that will be lucky is if they don't appear anywhere else in the file. Simple sanity check. Alright, they only appear in that space. Let's see what happens. Cannot do something. Oh no. Oh, if you read the oh boy. This is purely a Yosisism. I can't put an always block. Must we always have so many problems? Okay. Wow. It only allows you to use tri-states in these like question mark jobbies. So what I need to do is make a signal. Like my data would be this if I could do it. So let's call this one D out. Right? Is that really? Okay. 70 D out. Okay. Now what I'm going to do is I am going to get rid of that replicated code and use D out in here. Okay. I can't do that either. Therefore, I'm going to do this, actually. That way, D out always has a value. It's not a latch. D out is output from the FPGA in this context. So if I'm reading from memory, I will put the value from the ROM on D out. Otherwise, I will put the value from the SD card on it. And that'll be in here. Then what will happen is I will take that and say D equals D out, but only when I want... oh, this stinks. Almost. We keep this. We also need a wire D-bus direction. D out. D-bus direction. Okay. In here we will say, actually this is dumb. D-bus in or out. Okay. This is one if the FPGA is outputting to the data bus. Okay, so here's what I'm going to do. D-bus out is always false unless I have one of these situations where I need to send some data. in which case it becomes a 1. So now I have this idea is a multiplexer. It's either going to get a data from ROM data when the address is in range and the right cycle is taking place, or it's going to get its data from the SD card bits on the FPGA when we're in an I/O request on port F0. In both cases, data output is a 1, so I know I need to drive the bus. If neither of these is being done, data out will stay 0, and then I can then go back and make Yosis happy by saying assign D equals, and then I can say if D out is true, assign it from, or rather if D bus out is true, use D out, else go high impedance, and this will satisfy the idea that, you know, Yosis only wants to do tri-state if it sees one of these question mark operators, the ternary operator. It has to have this pattern or it can't figure out how to do it. It was too complicated over here, okay? So this should now cover that error. You suck. Oh, what happened on line 124? That warning comes out no matter what, actually. What's wrong with this thing? The wire. I thought I could do a wire with a equals and have it act the same as a assignment. That may not be true. I think you can assign it an initial value. Oh, that's what you can do. It's like if you have an initial block. And I can't do this in open code like this either. I need to do it inside a process. Or assign. That should take care of that problem. Now what? Who the hell? Assign that equals. If all that crap is true, then it's a 1. Otherwise, it's a 0. This can't possibly be a precedence problem. And I do not know yet if this is the right value that will come out of the CPU. I may have to ask if only the lower half of the address bus is this, by the way. Equals. If that is true, then make it a 1, otherwise make it a 0. What's wrong with that thing? Assign wire equals thing. What's wrong? Is that not what that is? I should be able to use that as a conditional. But it might want me to do this and turn it into a Boolean operation. I can't believe that this is necessary. I can't wait to find out what's wrong with this thing. You stink. So now that's a 1 or a 0. No, that's a 1 or a 0 anyway. Give me a break. I don't need to do all that crap. So this is a 1 or a 0. This down here is a 1 or a 0. No. This is just no. Alright, so now I'm going to be lame. On 124, let's say we can't figure out what the heck is going on here. Now, a decent compiler will give you the line number where the error really is. And if I do something like that, the line number's changing. So if it doesn't like this, it should say line 126. Now, I don't know if it will, BIOS just doesn't have very good error messages. It's griping about 128, and it may very well be that that's where I'm at. Okay, if A is equal to hex F0, so what is A, and why is that not? Oh, wait a minute. I'm an idiot. I can't just put that might help. This is what happens when you're using different languages at the same time. This is dumb. I'm going to just do this because I'm sure that we're going to find out. We're using Z80 I/O instructions, and the upper half of the database is probably crap. So we don't want to look at it. This is what you really want to do. I'm sure it was right from the get-go. You don't have to put these ones and zeros on the end. Yeah, okay. Oh, boy. Timing analysis failed due to the presence of combinational loops. Especially timing ports, etc. Etc., huh?